making a group photo, and for departing to poster for underrated poster session. Okay, floor is yours, and it will be first steps. What is possible, what is not possible, navigating in the computational research of oxidation by ruthenium complex.
So this is very preliminary. I had not had very much time. I had a lot of help with Dimitri to continue this moving forward, but we'll show what we had for results. But first off, what I'm gonna discuss is that the whole purpose of this is to look at how we're having a power crisis in the world, not at this exact moment, but looking towards the future. I found data for 2007. There was 16.2 terawatts was being used worldwide. But they're estimating through U.S. Power consumption by 2050, with the population increase, we will probably hit 106 terawatts of energy being used per year. If we keep increasing by this rate, at some point we will hit a maximum where we cannot keep producing power with the current standards. So we were looking at renewable sources because as of right now we're using a lot of fossil fuels. One of the renewable sources is solar power. But solar power, we generate the power, but we're very incapable of storing this energy. So we use it as we make it, but come night, we don't have that energy anymore, so we need to figure a way to fix this. So one way of fixing this is looking at chemical energy storage, and one way is by looking at water oxidation. One way of water oxidation is that we're looking at electrolysis, and that is splitting the water with putting a current through the solution, and we will end up getting oxygen gas and protons. Then if we get to the cathode, those protons in solution will then be combined with 2 electrons forming hydrogen, which then with these can then go through the process of a hydrogen fuel cell, where we combine these hydrogen and oxygen and form water as a byproduct while giving off energy. So one way, some ways to do this, electrolysis is not a very green way if we look at the current standards of making energy, because it requires a lot of power to do this process. So one way to help with this is by creating catalysts.
Your call will be disconnected.
How much energy requires to do the water oxidation. I know Dr. Rogers probably doesn't like this image because it's not showing the best of the structure. And the course time ended. Well, that was my presentation.
Why is it tied into the?
Because he videotapes them.
Tris-BP ruthenium-2 is a flat molecule?
No.
Okay.
Yeah, that's the reason I said you wouldn't like that. It was a quick and dirty structure. I know it's. I do not know the terminology of it. I have another figure right next to it of another system. We used instead of a Tris-BP, we just used 2 bipyridines in it, shown here. But a tripyridine would then have this remote's evil. We'd have another bipyridine going that way in the plane, and that is what it would be. I know I could do a better job drawing that out through ChemDraw. It's just that's what I did to quickly show. We use this here. Do not know exactly how to pronounce that because I just know Tris-BP and stuff. But this is a 2-bipyridine system, and we use that because we realized that through certain methods of doing molecular dynamics, the bipyridines can get in the way of the water molecule getting to the ruthenium through what methods we were trying to do. First off, I was using the Tris-BP for these right here for the density states. I'm not meant the
level routine. What is precedence level routine?
Keep talking.
Yeah. Okay. So.
Tell your story.
Yeah. So I created density states using the Tris-bipyridine system that I got from Dimitri, and not much was given from that. It's just a quick calculation I moved forward with, just showing the homo-lumen gaps and spin polarized density states for the ruthenium 3 cation. Just to keep this things moving forward. So as I said, we use a 2-bipyridine system here to run these molecular dynamics. We, as Dimitri calls it, evolution is just by heating up the sample, just naturally and just letting the water molecules move around and hopefully strike the ruthenium. That's why we remove one of the bipyridines to help facilitate the water actually hitting. What we've realized is that it's not as easy as it seems, as you can see over the technical problems. So this is just how let's see if this one works. Yeah, okay. So we do get oxos.
Try another one.
Yeah, it's just we do have oxygens of hydroxyls formed. I know a little bit, but it's very quick because how much time it takes to create these. But this is with the 6+ cation. This is also to help facilitate to see if we can get the water oxidation to occur. We are struggling in getting this to occur. But to keep moving forward, I'll show it. These are also run at 1300 Kelvin. We also then had other versions of being created. And all of them, we really did not actually see any of the water oxidation occurring in a lot of these. Not entirely sure why these weren't. But what we're going to try to move forward with is what we call creationism. Okay, let's get this done. Creationism, which is by what Braden did, is this by taking the water molecule and then giving it an initial velocity towards the ruthenium center to hopefully facilitate the. This is definitely one of the most interesting presentations to have. To hopefully facilitate the water oxidation that occurred, we were struggling to get it with the system just by heating. We'll just call it questions at this point.
Well done, Christian. And we have 6 minutes for questions, group photo, and departing to another meeting. Please.
So, I mean, how can you interpret your creationism physically?
Physically, I didn't really think about that too much. Physically, what we're hoping for is that there's in an actual reaction solution, we have a lot more than just 11 water molecules surrounding the ruthenium catalyst. So we will probably have a lot higher chances of that actually striking than versus the evolution path of 11 molecules. So by using creationism, we just basically guarantee one of them actually hitting in a correct orientation.
Alisa?
I just have a simple question. I must have missed it. What is your conclusion?
That we need a lot more work to really prove it much. But right now our conclusion is that we are not getting any significant products of logic. If you look at very closely at some of these, we get some interesting bonds going on, especially in the 6+ cation. That I did witness a triple bonded hydrogen. Yeah. So very interesting data is shown. But that's the reason I wanted to move forward with creationism. I just didn't have enough time. Yeah, right. Just didn't have enough time to create the files and run it, and that's what happened.
What are the other 2 ligands you're putting in your ruthenium with bipyridine?
Tell by words.
What?
Tell by words.
Yeah. I believe we just took the bipyridine off and then just added hydroxyls to it. Just it's
ruthenium gets bipyridine, gets hydroxyl.
Is that what you say? This? Yeah. Okay.
11 traces bis, yes.
Oh, okay. I was trying to remember, but yeah. So it would be. I know the titles are wrong. I was creating this in a third.
What oxidation state is that in?
So the first one was in 6, 6+.
Ruthenium 6?
It was just.
Or ruthenium is hydroxide, so ruthenium 8.
Okay. we just the reason I say 6 is because what we did is we pulled out 6 electrons from the system.
So ruthenium 6, so it's going to be net +4 cation.
Yeah.
And you couldn't get it to oxidize water?
I think I just.
What is the? Let me contribute to the discussion. What is a typical time rate for water oxidation reaction? On which time scale?
Ruthenium 6? I have no idea.
But in most optimal situation, or what range order of magnitude?
So it's a complicated answer.
Yeah, that's a
But-
nod.
yes,
Multiple steps, some of which are slow.
Exactly,
some of
multiple
which are
steps,
fast.
and each of steps will take substantially longer time than this 100 femtosecond
Yeah.
short trajectories.
I think in one of the videos I did see hydrogens pop off.
But did you even see an OO bomb form?
We
Ruthenium 6, it should be ripping electrons out of whatever the heck you throw at it.
But the way he's doing this, right? He's just defining a trajectory
Yeah.
to the ruthenium center.
well, that's
Is
what
the
my hope of
ruthenium
next.
center coordinatively unsaturated when you do that, or does it still have two hydroxide
Well, it
ligands?
should be formed at the hydroxide ligand. We were just trying to the one you were doing, you weren't defining a path. You were just randomly fucking things at it, right?
Pretty much.
Yeah.
So, in the sake of time, we need to continue this discussion because it may seed productive research. But time is up. Let's thank all speakers. Announce them generous credit for their effort, and line up maybe near our guests for group photo. You can keep sitting. Be part of the computational group. Just line up along the wall. And you can keep the.
Yeah, I would like
We're
that.
ridiculous.
I would like that picture.
Daniel, come here.
Yeah.
Yeah, please. You contributed to the. If you
Should I be like that, alright?
add weight to this meeting. Can you please come? Oh, no, just we didn't take a picture.
Sure. Is everybody happy?
Not really.
I have like a thought, like you guys see the picture, it's too
Okay,
loud.
well.
Is it good?
Yes.
Okay.
Okay.
Okay, many thanks for everyone. And we are done with class. And Javid has some announcement.
And we have a birthday boy here, Braden. His birthday today.
They were handing out, but I
So we bring a cake. So
You want to delete
It
one?
melt. It must have already melted.
No, it
It's been
didn't
2
actually.
hours. How is it not melted? I mean, it's
Doesn't go that
inside.
bad.
Yeah, but it's inside chocolate. So you see, you eat
gotta
it, you're
eat
gonna
it
bite
over.
into it, and then it's gonna.
Well, they so you nibble up and then you just drink it.
Yeah.